Hey everybody, this is going to be a short and sweet video over 1.4 types of functions and their rates of change. So let's take a look at rate of change. So when you hear rate of change, the first thing you should be thinking of is slope of a line, or miles per gallon, feet per second. Did I say miles per gallon? I meant miles per hour. Something per gallon would be but more like maybe gallons per second, feet per second, so on and so forth. So those are the types of things that you should be thinking of as slope and some sort of ratio between one quantity and another quantity. So let's look at this first example. A car is initially located 30 miles north of the Texas border and is traveling north on Interstate 35 at 60 miles per hour. The distances between the automobile and the border are listed in the table. A scatter plot of the data is shown in figure 1.65. It suggests that a line that rises from left to right might model this data. So, elapsed time, 0 hours gone by, distance is 30. So that's where they said they started 30 miles north of the Texas border. After an hour, he moved 60 miles an hour, so he moved 60 miles. Now he's 90. Now he's 150, now he's 210, now he's 270, now he's 330. So you can see each hour increased, or each hour that goes by increases by 60 miles. You can see that if you graph it on a coordinate plane, that as you go up every 60 miles every hour, it creates a straight line. This is called a linear model. So anytime you have a straight line, that's what we call a linear function. And they represent the function here. F of x equals 60x plus 30. You guys are going to remember this from Algebra 1. This is known as the y-intercept, or the starting point. And this is known as the slope, or rate of change. And so we always referred to the number that was in front of the x value as the slope, and the number that was out there as the starting point, or the y-intercept. And you can see the reason we call it the y-intercept is because the y-intercept is where it crosses the y-axis, and it crosses the y-axis at 30, or starts at 30 in this problem here. If we look down at some definitions here, a function f represented by f of x equals mx plus b, where m and b are constants, is a linear function. Just what I described there. M, again, I'm going to point this out. They refer to m as the slope because you'll see some equations with m in it. And then b is the y-intercept, or the starting point. A function f represented by f of x equal b, where b is a constant fixed number, is a constant function. An example of this would be like f of x equals 2, f of x equals 10, f of x equals 15. What all these functions are saying is whatever the function input is, so no matter what I plug in, I'm getting a 2 out. No matter what I plug in, I'm getting a 10. No matter what I plug in, I'm getting a 15. So if we look at, like, let's say the domain of f of x equal 2, the domain is going to be negative infinity to infinity. We can plug anything in. That's what the domain is. The range, though, what are we getting out when we plug something in? The only thing we're getting out is 2. So we get a range that is just one number, 2. If we look at the values of the table here, every input gives you 2. And anytime all the inputs give you the number 2, you get a flat line at 2. What that means is the slope of this line is 0. So the slope is 0, meaning it doesn't slant at all on the graph. There's no tilt. It's a flat line. Think of it this way: like if somebody were to die, and when they die, their heart rate flat lines. They call it flat line. That means there is no slope there. There's no heartbeats for the amount of time passing. So the amount of time is passing this direction, but there's no heart rate bouncing up. So no tilt. This formula should look very familiar to you guys. This is the slope formula. The slope m is a real number that represents the tilt of a line. I've referred to the tilt numerous times now. It is a ratio between the change in y and x values of the function, also known as the rise over the run. The slope m of the line passing through the points x1, y1, and x2, y2 is the change in y over change in x. All that's saying change in y over change in x is just like the distance formula. So in the distance formula, when we had distance equals square root of x2 minus x1 squared plus y2 minus y1 squared. If you remember this distance formula we just did, we added this distance, which is the distance horizontally, so horizontal, and we added that with the vertical distance, and then took the square root of that, or squared both of those, and then took the square root, and that gave us our distance between the 2 points. That gave us this right here. That was our distance between the 2 points. We're not looking for the distance anymore. We're looking for the ratio between them. Like, is it rising faster than it's running, or is it running faster than it's rising? That's what we're looking for. So now instead of squaring these and adding them, we're going to take a ratio of them. That's this right here. This is the ratio of those two things. So in this problem right here, and what they're showing here is they're saying, okay, we want the change in y, which is y2 minus y1. That's no different than the distance formula. And then we want the change in x, which is x2 minus x1, which is the horizontal change in x. And then to figure this out, we divide them. We take the, okay, how much is this running, divided by how much, or how much is this rising, divided by how much this is running. For example, let's say that this is the number of miles, the y-axis, and this is the number of hours. Well, now when we subtract the y2 minus y1, we're getting the number of miles traveled, and we do the x2 minus x1, we're getting the number of hours. So when we take the miles divided by the hours, guess what we get? Miles per hour. So you can see how all that works. Let's take a look at these graphs down here. These are pretty standard. We always read everything from left to right. So as we read from left to right, and we get to this spot here, if you can imagine, we read from left to right. Now we're going up and to the right. So anytime we're going up and to the right, that is a positive slope. If we're going down and to the right, so as we move across left to right, and my pencil goes downwards as I go across this line, that is a negative slope. If I'm going across it and it's just completely flat, that is a zero slope, horizontal line. And then anytime I'm going up and down, that is an undefined slope. The reason that they say that that is undefined is because you are dividing by zero, meaning how far in the x direction are we going from side to side? Well, we're going zero, but we're dropping the whole time. So we're dividing by zero in our ratio. Anytime we divide by zero in the ratio, that is an undefined number. Okay, you can't divide by zero, but this line represents an undefined curve is what we would call it, undefined line. All right, let's calculate some slopes. So let's look at the first line they do here, and let's kind of look at this example, then we'll calculate our own. Find the slope of the line passing through the points -2, 3, and 1, -2. Plot these points together with the line. Explain what the slope indicates about the line. Okay, I plot -2 and -2, 3 here, and 1, -2 here. What they're going to tell us is they want us to take the change in y, which if you notice here, the change in y is -5. How do they get that? They take -3, not -3. Let's write these two coordinates down. -2, 3, and 1, -2. So they're going to take, for the y values, they're going to say, all right, this is y1, y2. This is x1 and x2. They're going to take -2 minus 3 over 1 minus -2. And so what they get there, for change in y, they ended up with -5 over the change in x, which is 3. And that's how they end up with their -5 and 3 here for a slope of negative 5/3, meaning this is going down 5 and over 3. Let's find a slope with 4, 6, and 2, 5. So again, I'm going to take x1, y1, x2, y2. And I'm going to take 6 minus 5 over, let me write this out here a little bit better. 6 minus 5 over 4 minus 2, which gives you 1 over 2. So slope is 1/2. Now I'm going to do 4 minus negative 2 over, so I did 4 minus negative 2 right here. This is x1, y1, x2, y2. Now I'm going to do, so I did 4 minus negative 2, and I'm going to do negative 1 minus 4. That's going to give me 6 over negative 5, so that's negative 6 over 5. And then down here I'm going to do negative 8 minus negative 8 over, let's see, 12 minus 7. That's going to give you a 0 over 5. So my slope is just 0. Okay? So that's how you do slope intercept, or that's how you find the slope of a line. All right, let's talk about interpreting the slope and iPod memory. So they give us a graph of iPod memory versus songs. And on the graph, you can see that the iPod memory starts at 0 gigabytes and the songs start at 0 songs. That makes perfect sense. That's if you have no gigabytes used, you haven't downloaded any songs yet. So let's go through the different questions they have here. Why is it reasonable for the graph to pass through the origin? Well, that makes sense of exactly what I just said there. The origin is 0, 0. This is our x value, which is the gigabytes. This is the y value, which is the songs. If you've downloaded 0 songs, then you've used 0 gigabytes on your iPod. So that's why it's reasonable. Find the slope of the line segment. If you want to find the slope of this line segment, let's write down the coordinates. This coordinate here is 80, comma 20,000. And the original coordinate is 0, 0. So what we're going to do is take 20,000 minus 0 over 80 minus 0. So we have 20,000 over 80. If you take 20,000 divided by 80, that's going to give you 250 songs. All right, this is the songs per gigabyte. So you end up with 250 songs per gigabyte. So that's our slope, meaning every gigabyte you use, you're gonna be able to store 250 songs. Let's look at the 4 different representations of basically a linear function. You can represent it verbally. You can see that the linear function can be represented with y equals, or multiply input x by 3/2 and add 3 to get the output y, which is written symbolically like this. So this is the verbal of multiply input x by 3/2 and add 3 to get the output of y. This is the symbolic version of that. Then you got a numerical version, which is your t-chart. I always talk about using a t-chart anytime you're trying to find domain and range. You can use the graph. So that's a numerical version of it. And then the graphical version would be these coordinates here and the numerical t-chart being plotted onto a coordinate plane. And you can see that you can represent, in the graphical version, you can use all of these. You can use obviously the line to represent it, a numerical table because you can see all the coordinates, and then also the function written out next to it to reinforce that linear function, what it looks like. Let's talk about nonlinear functions. So nonlinear functions are any function that is not straight, basically. So if a function is not linear, then it is called a nonlinear function. The graph of a nonlinear function is not a straight line. With a nonlinear function, it is possible for the input x to increase by 1 unit and the output y to change by different amounts. Nonlinear functions cannot be written in the form of y equals mx plus b. So all that's saying is, now that we have something that does not act like a linear function, we cannot use the equation for linear functions for these problems. So let's look at a t-chart of a nonlinear function. You can see the input for the nonlinear function is 0, 1, 2, 3, and 4, but the output goes from 0 to 1, which is an increase of 1, then to 4, which increases by 3, which then goes from 4 to 9, increases by 5, then to 7. You can see that the increase is not constant. So then you would have to go through and you'd have to figure out, okay, what kind of function is this? Well, this is the squared function. If you plug 0 in, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, and 4 squared is 16. So the larger the number for x, this function increases by a much larger factor. So this is an example of a nonlinear function. Your homework, just get started on it. Here's some examples of nonlinear functions some more. So you've got the square function, we just talked about that. We've got the square root function. We just talked about, well, if you look at the square root function, it basically will start at 0, 0, and then tail off in the northeast direction. And then obviously with different translations can look different than what this looks like. The cube function, it is going to kind of makes a little bit of an S, but it's reflective about the origin. And you can see that it's obviously not straight. The absolute value function would be the closest to a linear function because it's a straight line. It basically makes a V, so it's got a straight line from negative infinity to 0, and then a straight line, and this is decreasing, and then a straight line that is increasing from 0 to infinity. So this is the absolute value function. These are all four, these are basically the 4 types of nonlinear functions. Increasing and decreasing functions. So it's kind of self-explanatory what an increasing and a decreasing function is. If you read from left to right and you see the graph going downwards as you read from left to right, that's a decreasing function. If you see it going upwards, like toward the northeast, that is an increasing function. So let's look at this example. This is rock music's share of all U.S. sales, and it's a percentage. So between 1990 and 2001, rock music sales decreased from 36% to 24% of all music sales. So we say that that function decreases for 1990 less than X less than 2001. What they're saying is from this point right here to this point right here, you can see that this is decreasing in sales from 36% all the way down to 24%. But between 2001 and 2006, rock music sales increased from 24% to 34%. So you can see at this point right here, rock music sales began to increase. And you can see that because this is moving to the northeast. So as we move in the X direction, from 1990 to 2001, you can see that the sales decreased, meaning our function is decreasing here. And then right here it bottoms out and it starts to increase there to 2006. So that's basically the concept of increasing and decreasing functions. These two interval notations basically describe to you when it's increasing and when it's decreasing. So from 1990, so when X is between 1990 and 2001, you are decreasing in sales, but from 2001 to 2006, you're increasing. So we'll be doing, you have a lot of problems that ask you to state when something is increasing and decreasing, and that's what they're looking for. They're looking for when the function is increasing or decreasing and what domain values make the function increase and decrease. So recognizing these, let's take a look at the absolute value function. So the absolute value function is decreasing from -4, so we'd say decreasing from -4, well, this could go on forever in this direction, so that's really negative infinity, all the way up to 0. And then it's increasing from 0 all the way up to infinity. And then this is for x values. I should state that this is x values where it's increasing, so domain values. If you look at the cubic function, it's increasing from negative infinity to 0, and then it's, let's see here. Yeah, it's increasing from negative infinity to 0, but it never stops really increasing. Right here it flattens out and then continues to increase this direction. So it's going to increase then from 0 to infinity. So instead of decrease, I should say increase there. So it's increasing the whole time from 0 to infinity. And then with our square root function, this is an increasing function, and it increases from 0 to infinity. As you go from left to right, this function continues to get larger and larger and larger, or the range values continue to get larger. There's a definition at the bottom which kind of explains how to tell when something's increasing and decreasing. It says that suppose that a function f is defined over an open interval f on the number line. If x1 and x2 are in I, so in the interval, f decreases on I if whenever x1 is less than x2, f of x1 is less than f of x2. What this means is if the domain value x1 is less than the x2 value, so this is a smaller number than this number, but the output of f of x1 is also less than the output of f of x2, you have an increasing function. So if your domain value is less than your other domain value, and then the output of the first domain value is also less than the output of the second domain value, then you have an increasing function, which should make sense because if you have, let's say we have the function x plus 3, and I have f of 1 then would be 4, and f of 2 would be 5. Well, my original x1 value is less than my x2 value, and my output for f of x1 is 4 and f of x2 is 5. So my output for the initial domain function or domain value would be 4, and my output for my second domain value is 5. You can see that they're less than, so this is an increasing function. Whereas if you have f of x equals x minus 3, now I try f of 1 and f of 2. F of 1 is 1 minus 3, which is negative 2. F of 2 is 2 minus 3, which is negative 1. Oop, I messed that up. This should be negative x. Let's try that again. So I plug in 1. I get negative 1 minus 3, which is negative 4. I plug in 2, which is negative 2 minus 3, which is negative 5. Okay. Now we have a decreasing function here. And I know it's decreasing because in the second part it says if x1 is less than x2, so x1 less than x2, so 1 is less than 2, but my output for x1 is bigger than the output for x2. So my output for x1 is negative 4. Negative 4 is a bigger number than negative 5. So I know that right now I have a decreasing function there based on the definition. If we look at more increasing and decreasing functions, you can see here an explanation, x1 is less than x2, and you have the function of x1, the output here, being also less than the function of x2. That's how we know it's decreasing. x1 less than x2 here, but the output of the function is bigger with the input domain of x1 than it is with the input domain of x2, so we have a decreasing function. And then you can tell as you go across here, they have a function here where as you go across, you can see the guy here, he's decreasing, so he's walking down the slope. That's a decreasing function. And this person is walking up the slope, so that's an increasing function. Interval notation, I think we should all basically know interval notation. I'm just going to allow you to look over this. Parentheses, you cannot equal those numbers whenever you use parentheses. If you use a bracket, you can equal those numbers. So you'll see here that this is less than or equal to, so x is less than or equal to 3. We can throw a bracket on that. But in this situation, you have -2 less than x less than 2. You put parentheses saying we're going from -2 to 2, but we cannot be -2 and we can't be 2. So I'm going to let you guys look over interval notation. We've gone over that in Algebra 1. You guys should be familiar with that. Average rate of change. I'm not going to go over this much. The average rate of change is simply the slope. But for nonlinear functions, because they are not straight lines, there is not a definite slope. Whenever you want to find the slope of a nonlinear function, the best you can do is pick 2 points on the curve and then find the straight line slope between those 2 points and then call that the average rate of change. So you're just basically saying this is roughly what it's changing at, even though it's not going to be exact. You find it the exact same way. It's still the ratio of change in y over change in x. So really the formula doesn't change there. You just pick 2 points that are on that that are on the graph on that nonlinear function and then find the slope between them. They show a couple of examples here. So you've got x2, y2. They picked a point here. They picked a point where it's flat. And they said, okay, what was the rate of change here? So you can see that this function is turning and it's not straight, but it ends in this spot and begins here. So they would take y2 minus y1 over x2 minus x1 and say, all right, this thing is roughly changing at this rate. A numerical example of this is you've got this looks like an x squared function. So you've got 21 or 1 comma 21 is one point that's on the graph. You got 0.5 comma 2 is another point. They take 21 minus 2 over 1 minus 0.5. That gives you 19 over 0.5, which gives you 38, which is how they got their slope. So the average speed of the car from 0.5 to 1 hour is 38 miles per hour. So this was a distance or time versus distance graph, and you can see that roughly the change in speed over that half hour, or roughly the speed of that car over that half hour was 38 miles per hour.